Good afternoon. All right, second lecture. The last time we spoke about chemical reactions, and I demonstrated a chemical reaction to you. I shown the reaction of hydrogen with oxygen to you, and we had some fun with exploding balloons. And what we have seen is that two parts of hydrogen react with one part of oxygen to form two parts of water. And this was quite a vivid reaction. It was an exothermic reaction. It was an explosion. So the reactants, hydrogen and oxygen, they had an initial energy, if this is our energy scale, and then, I got to be careful not to hit Karen, and then we had to give it a little kick. We had to overcome the activation barrier. I could have used a very small flame, but first of all, I don't have a small flame. I don't want to be so close to the balloon with the small flame. And I needed a larger flame to melt the encasing of that. That's the balloon, all right? If I used a small flame, we would have had the same effect. So you just needed to get a couple of molecules acting with each other to form water. Then they release energy, and that energy will overcome, for the rest of all the molecules, the activation barrier, okay? So what I haven't done to you, or what I haven't shown to you the last time, is that we can make soap bubbles, and these soap bubbles contain hydrogen, and then we blow up soap bubbles. That's especially fun. Itsy-witsy teeny soap bubbles will blow you out of your seat, probably, okay? And so then we add more and more oxygen. And when it will be the loudest, then we know we have reached the stoichiometric ratio. The ratio is 2 moles of hydrogen to 1 mole of oxygen, and the water will just evaporate into the air. And let's do that now. So I hope I'm in good shape here, because it's not easy. So we have hydrogen here now, and we slowly add oxygen to them. Okay, that's it. Let's add some oxygen. So you see, a little bit more, a little bit more. Aha, the oxygen is coming. Itsy-witsy teeny weeny soap bubbles here. It blows out my flame, okay? You see, we have now a ratio, careful, 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 of 2 to 1. Let's go a little higher here. Whoa! So the ratio is varying, obviously. All right, that's it. Thank you, Karen. So this is stoichiometry as its finest here, okay? So we have exactly the right ratio. That's what stoichiometry is all about, okay? And then we introduce the concept of a mole. And we say a mole is a unit. A mole means 6.022 times 10 to the 23rd something. You get a mole of people. I hope it will never happen, okay? That would be absolute chaos. There would be everywhere people in the world. More than that, there would be hundreds of miles high, actually. Very tall people. So we know that our secret language, 1 mole in chemistry, when we talk about a mole, we always mean atoms or molecules. But you could get a mole of shoes, a mole of people, like a dozen donuts or a baker's dozen. It's just a unit. And we don't want to say 6.0222 times 10 to the 23rd. We say 1 mole. And we know that 12 grams of the isotope carbon-12 contains exactly 1 mole. If something is double as heavy than carbon-12, then double the mass contains exactly 1 mole. All right? And so we measure everything relative to our standard, to these 12 grams of carbon-12. All right? So that way we can get our molar masses. They're in the periodic table. They are listed here. The molar mass of carbon is 12.011. 12.011. So carbon doesn't contain only carbon-12. Natural carbon contains carbon-13 and carbon-14, about 1% of carbon-13 and 0.1 or 0.2% of carbon-14. All right? A very small amount. Carbon-14 is radioactive. So we also, I hope Karen comes back soon, we also have seen, and I talked about this reaction barrier, we want to make a hydrogen car. So you use hydrogen and the oxygen from the air you take, you enrich it a little bit in a device in your car, and then water comes out of your exhaust. That would be ideal, okay? And so, but you don't want to have a car where you have explosions like this. Nevertheless, in your car now, the explosions are pretty heavy too, but not quite as heavy as you see that. So you would like to have a little more continuous reaction. And that the secret lies in lowering this reaction barrier, okay? This transition barrier. And that means we need to lower this, and we can lower the activation energy by using a catalyst. We use a surface, and the reaction happens on that surface, and somehow it happens that we don't need that much starting energy. Let's do that now. I'm going to show you a catalyst. The catalyst is, if we could have the picture up here. Good. So I see myself here. I need that monitor here. Okay. No, up there. So this is our... Which camera am I on? This one? Okay, good. So then, like in television, when they look at the wrong camera, happens all the time. So this is this piece of platinum, and now if you could show that nozzle here, out of this nozzle, we will extrude hydrogen gas. And so, of course, we need to have a little bit of activation energy still, not quite as much. So we will heat up this piece of platinum a little bit, and then hold it in front of it, and you see how smoothly the reaction happens between hydrogen and oxygen from the room, hydrogen from the nozzle, oxygen from the room, and you will see this glowing, because that's an exothermic reaction. It wasn't glowing before. Karen has to warm it up a little bit, but it's not glowing, and then you will see it glowing, and the reaction will go on. Okay? Let's have a look at this. See that? The hydrogen coming out of the nozzle on the surface of the catalyst that makes water, catches the oxygen from the air, or which is absorbed on the platinum catalyst, and there it is. It maintains that reaction. Isn't that beautiful? That's how you could take a car. You take that heat and then make it into energy, translational energy. Okay? Good, that's it. Thank you very much, Karen. That was very impressive. So we have lowered the activation energy barrier. You will never get it totally lowered because this is in the nature of that reaction. Okay? So let me ask you a question. We have 1 mole of hydrogen. This is the reaction. I always leave this up here on the left side. That's what you need for the lecture, for that particular lecture. And you can look at it. It will help you answering some of the questions. There will be some data there that will help you answer the question. We have 1 mole of hydrogen and 2 moles of oxygen. According to this reaction, we make water. Okay? Now, we react all the hydrogen with all the oxygen, and then we have a certain amount of water, certain moles of water, certain moles of oxygen, or certain moles of hydrogen. Is there anything left over except the water? And the question is, Which species at the end of the reaction has the greatest number of moles? Hydrogen, oxygen, or water? Why don't you think about this and give me your answer? So with the iClicker, if you haven't registered even on Monday or next Wednesday, it really doesn't matter. As long as you click, we get you. We don't know who you are because you haven't registered, and you can register at any time. It would be good to register next week, but if you don't get around to it or you don't have the iClicker number in the back because your body has used it so much that it wore off, then you just register, you just click it, and then we have a program which is not working actually, but we are able to get you the ID number, supposedly, of the iClicker where there is no number on there. Okay? You have to come to me after lecture. I'm not so sure if it works. I tried it. I couldn't get it to work. But we will eventually get it to work. So I usually give you 2 minutes for this here. At the moment, it's very long because the questions are rather simple. Later, the questions will be a little bit more complex, and you will need these 2 minutes for you to think and give me the right answer. Discussion is in the second round, okay? The first round, you test yourself, if you can do it by yourself. And nobody knows what you clicked in there, okay? Not even I. I could look it up, but it would be too much work. And your identity here is your student ID, okay? Your student ID. You register your student ID, not the number what you gave your web page or your email. It used to be the student ID, actually, but now you can take any name that you want. But here, if it says register, you give me your student ID. That key is the entity that we have on you for as long as you study. Aha, we have 31% who say A and B and C, and we have 63% who say B. Usually, if I'm below 20% wrong, I don't redo it, okay? But this time, I'm going to redo it. I gave it away already, all right? So why don't you think about this again and discuss this with your neighbor and try to give me 100% right answer, all righty? Please discuss it with your neighbor, the person behind and below, above you. What is it? Vote again. What's the answer? Okay, 137. So we have 17% who don't agree with the right answer, which is most likely, let's see if we can get that flame going here. Okay, it's glowing now. And now we come to the solution. And the solution is you have 2 moles. This is your stoichiometric equation. That's a balanced equation. 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. But what do you have? You have 1 mole of hydrogen and 2 moles of oxygen. How much? You have 1 mole of hydrogen. How many moles of water do you make? 1 mole of water. And the oxygen, how many? You have 2 moles. How many moles you need for this to react completely? Half of it, exactly. So what do you have left over? 1.5 moles. And with this, so this is the 1 mole, and this is the 2 moles, and now they react, and they form 1 mole of water, and 1.5 mole of oxygen are left over. That's an incomplete reaction, but it's complete as such because all the hydrogen was used up, okay? So 1 mole of hydrogen consumes half a mole of oxygen and produces 1 mole of hydrogen, and the question was which one is the most left over, and this was B, okay. Now, today we're going to talk about the nucleus a little bit more, and the atom, and then I'm going to introduce you to the way how you get these relative masses. We talked about the relative masses, and we talk about mass spectrometry. So if we look at the nucleus you all know that it must be positively charged because the electrons are negative, and you have the same number of electrons and the number of positive charges in the nucleus, and you have a neutral atom, okay? Now, if I say the radius of the atom, how large do you think an atom would be in meters? We're talking about nanometers. It's actually 10 to minus 10 meters about, okay, an atom, an average atom. And so you think, no, I'm talking about the atom. And the nucleus, what do you think the nucleus, how big it is compared to the whole atom? 10 to the minus 15 about, yeah? That's correct, all right? Meter. So if this would be, you see that quarter here? If you say this is 1 centimeter, then the outermost electrons would be about 1 kilometer away. Where would that be about? At the Berkeley BART station, okay? So if this is your nucleus, this quarter here, this quarter is your nucleus, that would be, thank you, John, this is it's about 1 centimeter, okay? A little bit larger, but let's assume we're doing estimation. About 1 centimeter. So the outermost electrons would be at the BART station, so that's where the orbitals are. Most of there's a big void there, okay? Because there's nothing in between. The electrons, they're zipping around here like crazy. We never know really where it is exactly. And it's not like you learned in school where this is like a ball on a string, which is the electrons. That's not what happens, okay? There's a function, a function of distribution of the electrons, and we learn about that. So, but all the mass is where? In the tiny little nucleus. And so why is the nucleus positive charged, and how did they find out that the nucleus is positively charged? So in the beginning of the 20th century, they didn't know much about the nucleus. They knew about the electron a little bit, but not much about the nucleus, and they discovered that there is this thing of radioactivity, this phenomenon of radioactivity, and then they seen that this must come out of the nucleus. The nucleus is unstable and spits out some kind of a particle, and they called this first particle alpha particle, because in the Greek alphabet, that's the first letter. And the second they called beta, and the third gamma, and then they found out it wasn't a particle, the third one. Okay, but we get to this later, hopefully. So you have this alpha particle, and alpha particles are helium nuclei. This helium without the 2 electrons. So they are positively charged helium nuclei. So Rutherford in 1919 said, you know, I know that these positively charged particles come out at this radioactive decay, alpha decaying material. So maybe I can use this to figure out if the nucleus is charged or not. So what he did, he used gold nuclei. He didn't use nuclei, he used very thin gold, and he used gold because he can make leaf gold. You can actually look through gold. Yeah? You make it so thin that you can nearly look through it. And he put his radioactive source here, and the leaf gold, the little piece of gold, which right here. And then you have energy. When they get emitted, these alpha particles from the nucleus, they have energy, kinetic energy, and they move forward. And so it moves towards that silver foil, and some of them went right through, some of them were deflected, which is okay. He said there must be some scattering. And he had, what you see here, he had a zinc sulfide screen, which when it gets hit by energetic particles, it lights up. Okay? The zinc sulfide is a phosphorus, and it lights up. So he said he has light spots here, and here, and here, and here, and he could explain that. But suddenly, he sees light spots in the front of that gold foil. And with this, he concluded there must be a charge equally positive than the helium nucleus, because equal charges, they repel each other. And the only way that he could get this, because it was so thin, is that the helium particle hits that nucleus here, and the positive charge repels it. And it can go even in the forward in the backward direction. So this is how he established that the nucleus has positive charge. We know that because who carries the positive charge in the nucleus? Or what carries the positive charge in the nucleus? The proton. Okay? That's the proton. And so we have protons, and the number of protons that you have determine exactly what element you have. If you have one proton, it's what? Hydrogen. If you have two, and if it's 92, it's uranium. and so 92 is right here, it's uranium. So this is the atomic number. This is the number of protons. And the protons have a mass. But there's another particle in the nucleus. What are they called? Neutrons. So the name says neutral, neutrons. They have no charge. But they have about the same mass than the proton. So you write, when you have, for example, hydrogen, you would here write H, and then the number of protons would be set here, okay? The number of protons, in this case, it would be 1. And then you have the isotopic number, which is the nucleon number. What's the nucleon number? It's the sum of the protons and neutrons in that nucleus. So what would be the nucleon number for hydrogen? Do we have any neutrons in hydrogen? No. So what would be here? C plus 0 would be 1. So it would be 1, 1. But there's an isotope which has a proton and a neutron. Anybody knows what we call that? Deuterium. It's double as heavy as regular hydrogen. Chemically, it behaves like hydrogen because it only has one proton. All right? So what would you write here? You would write here 1, and here 2. 1 proton, 1 neutron. All right, you got it. So, and then there's another one which has actually 2 neutrons and 1 proton. What would that be? That would have the number 3 here. What would that be? The biologists, they will use it a lot. Tritium. Okay? Tritium. Heavy, heavy hydrogen. Right? And they are about 3 times as heavy than the regular hydrogen, because the mass of the protons and the neutrons is about the same, not quite. Right? So this is the mass, and now you will understand why we use that atomic mass unit. because we don't want to write always 1.6262 whatever 10 to the minus 27 kilograms for the proton mass. And you see the neutron mass is a slight little bit heavier, more. It's in the 1, 2, 3, right here it is a little bit heavier. So this is 1.00728 atomic mass units, and this is 1.00866. We know that the charge for the proton is 1, for the neutron is 0. Now look at the mass compared to the neutron or the proton of 1 electron. This is 10 to the 30th, about 9 times 10 to the minus 31 is about 10 to the 30th, and this is 10 to the 27. So it's 1,000 times lighter, okay? So you need 1,000 electrons, which you don't get, to get the mass of 1 neutron. So essentially, the mass of an element is the number of protons and neutrons, the mass of the neutrons and neutrons and protons, okay? But you cannot neglect the mass of the electrons, because they have some mass, and we are able to measure masses in very, very small quantities. We are able to measure these differences with the mass spectrometers that I will be describing to you in a little moment here. But let's talk a little bit more about the nucleus. Now, some of you should be skeptical. They said he tells us that equal charges repel each other. So if I, for example, have lithium, how many protons do I have there? 3. So I have 3 positive charges in the nucleus, but they should be falling apart. They should be not forming a nucleus. So why do you think they stay together? Any heard of the 4 elementary forces? No. There's the strong force, the weak force, gravitation, and the electromagnetic force. Okay, you ever heard of those? It's the strong force. It's a very strong force which has a very short reach. The reach is about the diameter of 1 proton or a neutron. This holds it together. You know what carries the strong force? Gluons. Gluons. Glue. That's the glue. That's where the word comes from. That's the glue between the protons and the neutrons. It's gluons. And gluons are made out of what? Quarks, essentially, okay? Protons and neutrons are made out of quarks, and the gluons holds it all together. That's the carrier of the strong force. So there's a lot of quarks, but for us at this class, we are just interested in 2. Not even in this class, but I want you to be interested in 2. These are the up quark and the down quark. There's another 5, even 6. So the up quark has a charge, is 2/3 of the elementary charge. And the down quark has a negative charge, is minus 1/3 of the elementary charge. So how many up and down, and what kind of combination of up and down quarks would you need to make 1 proton? How would you make one? The charge is 1, isn't it, for the proton? How would you do that? You take 2 up quarks, that is 2/3, plus 2/3 is 4/3, minus 1/3 is 3/3, that's 1 times the elementary charge. Okay? So you have 2 ups and 1 down. So now I'm asking you, how do you make the neutron? 1 up and 2 down. Exactly, there it is. So the proton is up, up, down, and the neutron is up, down, down. All right? That's as far as you need to know about the nucleus at this point. So we talked about isotopes. Now, deuterium and tritium are isotopes of hydrogen. So the same way, you can have oxygen. Oxygen has lighter isotopes, oxygen 15, but there is also heavier isotopes, oxygen 18. Very little oxygen 18 in natural oxygen in air, but there is a difference. So if it's heavier and you evaporate water, you have H2O with oxygen 16 and H2O with oxygen 18. Which one would be easier to evaporate? the lighter one, okay? So if you have a certain temperature, and now we're going to make a temperature gauge out of this. If you have a certain temperature, the water will be in equilibrium with the water vapor above. There's water vapor here in the room, okay? And so there is a certain ratio of H2O 16 and H2O 18. Now, if I increase the temperature, this ratio will be changing. You will have more, the same amount of H2O 16, but you will have more H2O 18 in there. So that ratio changes if you increase the temperature, and it changes in the opposite direction if you decrease the temperature, okay? So when it rains, and I collect that rain, and then I make an analysis of oxygen 16 to oxygen 18, and I know what the right ratio at a certain temperature is, I could calibrate that, then I have a thermometer. So, but the thermometer would be just for this time. But we are interested, or we are the climatologists, we are interested in what was the temperature hundreds and thousands of years ago. So what we do, we find a place where the rain comes down as snow, and then it freezes, and it never goes away. That used to be the case, but it's not quite anymore. And then they have periods where it doesn't rain, which they call summer, and then they have winter. It depends if you're on the North or on the South Pole. And then they have winter. It's still summer or winter, but it's at different times. And so then the next winter comes, it snows again, and deposits the layer becomes to ice, and now all I have to do, there's this huge ice shield, I go and drill in this ice shield, I make a little core, not a little, a very large core, I drill into it and pull a long, long round piece of ice out of there. And this is how these ice cores look like. See, this is his tent here, this guy did that, they have a station there, and so the ice core lays here, see that's the ice, and so what they do, they take samples, and they can see actually very well when the season changed again, from winter to summer and so on. So we have an imprint of the oxygen 16 to the oxygen 18 ratio, and with this you can say what the temperature was in the past. And so this is, for example, the temperature up to 400,000 years ago. And you see there was always warm periods, then it was colder, then warmer again, colder, warmer, colder. That was a very short cold period, not in our times, but in the geologic times. And now this is where we are now. So we are here, and we are supposedly increasing in temperature, and I do believe this. Nevertheless, this guy here, Evans, from the Australian Greenhouse Office, I think he retired, and he became a consultant now. So he changed his tune, because he could show, not really very well, that from 2004 to 2008, there was a tiny little decrease in temperature. And he said, you know, this cannot be causing the greenhouse effect. I beg to differ, okay? This is not, if you have 4 years of records, it's not good enough, all right? So I do believe that this greenhouse effect, the temperature increase, is not only by this, the natural effect caused, but by the increased greenhouse effect of the emission of carbon dioxide that we have at this point, all right? So, on the other hand, let's see if we do something about this, okay? And you're going to have to deal with this very quickly, much quicker than you think. So by 2050, they say the temperature is rising by a certain amount, so we will be, probably we are pretty high here, but the Berkeley Pier will be a lot closer then. And so you could take the ship into San Francisco, if it's still some parts of it there, the hills will be there, okay? And so, I'm exaggerating. And so the point is, if the people are, we should deal with this in terms of saving energy, making cleaner energy, thinking about using energy resources responsibly. And then we have in 2050, we see, oh, we were wrong, but we have created a beautiful system. We have really created something new, not what our forefathers did. We created new energy ways of dealing with energy, much more efficient and so on. So we were wrong. If the other guys were wrong, who don't believe in global warming, you can kiss your whatever goodbye, okay? Because there is no return. And so I don't want to gamble. I just want to make sure that that there is good indicators that there is global warming, we should take care of that. And maybe we are wrong, but we will find out, and we have created something positive. That's how I see that, all right? So we have these relations here. Now, how do we get these relative masses? You use a mass spectrometer, and getting a mass of 1, 2, 3, or 5, or 50, or 92 is not a big deal. But these mass spectrometers, I explained to you the principle, but these mass spectrometers, they can get a billionth of a mass, actually. They are so sensitive, they can get a billionth of a mass unit, all right? So how does this work? You have your sample. For example, you calibrate your sample with a weight amount of carbon-12. You calibrate your spectrometer. A weigh out amount of carbon-12. I know exactly how many atoms I have in there, okay? And then you run it through your mass spectrometer, and then you get a peak, and you get also a signal height. And the signal height gives you how many atoms you have of it, and the location of the peak gives you the mass, how much mass you have. So let's see how this works. We have our sample, and we have, weight is of course, we ionize that sample. That means we rip off some electrons, all right? Now, the sample is positively charged. We put it in a gas phase, of course, and it's positively charged. The whole thing happens in vacuum, that there's no oxygen interfering. So this is positively charged, and now, if you have a positive charge, you can accelerate it, that beam of whatever you're making here, you accelerate it with a negative charge, and then you put it through a magnet. And charged particles are deflected in a magnet. It's actually a mass-to-charge ratio, but that's too complicated, okay? Yeah. And so the lighter it is, the more deflected it is. And the heavier it is, the less deflects. And so at the end, you have, like you sort them. I have that many particles with this mass, and that many particles with that mass. Let's do that. So there's our sample. This is a light sample. Boom, it hits our detector, and we get a signal. This will tell us the mass number here, and this will tell us the intensity, how many of them we have there. Now we take a heavier particle, or a heavier mass, compound. We run it through there. Big guy here. And there it is, doesn't deflect quite as well, and we get our signal. That's how this works. That's that simple, right? It's not quite that simple, but this is the principle of it. So if we would have hydrogen, and we plot our mass here, from 0 to 50. I just arbitrarily stop at 50. So what would we have at mass 1? Hydrogen, exactly. So we have at mass 2. What would that be? Helium. Would that be helium? What is helium? What's the mass of helium? Okay. All right. So it would be either heavy hydrogen, deuterium, or a hydrogen molecule. Yeah? That would be the hydrogen molecule, and this would be deuterium. Now let's go to mass 3. What would be that? That could be helium-3. All right, not helium-4, but helium-3. Or it could be the combination of molecule. This is hydrogen and deuterium, would be mass 3. Now, we go to mass 12. What would that be? Come on. Carbon-12, okay? And mass 13 would be? Carbon-13. And then we have mass 16. What would that be? Oxygen. And mass 18? Could be oxygen, or? What has mass 18? Oxygen plus 2 light ones? Water, exactly. You have H2O 16 or oxygen 18. Now, if you go to mass 20, what could that be? Mass 20, I don't have it here. Mass 20 could be hydrogen, water with hydrogen, and oxygen 18 would be mass 20. So now we have mass 32, could be to an oxygen molecule, or mass 34 would be oxygen 16, oxygen 18, or oxygen 18 would be a molecule of oxygen 18. Now CO2, mass of carbon is 12, mass of oxygen is 16. This is 2 times 16 is 32, plus 12 must be 44. 1, 2, 3, 4. Yeah, I did it right. 44. Now, if you have carbon 13 and oxygen, you can have CO2 with carbon 13. This would be mass 45. So you get the hang of it? Yes? All right. So we can determine extremely small fractions of masses with mass spectrometers. So we had talked about how these masses are then, the molecular masses add up to, the masses of atoms add up to molecules, and so we talked about this the last time. So now I'm going to ask you a question. We have an equimolar mixture of oxygen atomic isotopes, and what kind of equimolar mixture? So that is not natural oxygen. So we have oxygen 16 and oxygen 18, and we have the same number of molecules of oxygen 16 and 18, okay? And we run this now through a mass spectrometer. We run this through a mass spectrometer, and then we get a mass spectrum. You know that on the x-axis you have the mass itself, and the intensity gives you the number of particles or the number of molecules or the number of atoms, okay? So this is relative to each other. So if you have oxygen 16 and oxygen 18 at equimolar concentrations, and you run this through a mass spectrometer, do you get spectrum A, spectrum B, or spectrum C? Why don't you think about this and try to give me your answer? What is it? That's why we're doing it. Think about it. It's a statistical distribution, okay? Some of you had statistics already. Statistical distribution. And you can do statistical distribution. Perfectly distributed statistically are chemical systems because they have such large number of atoms or molecules or particles. They are perfectly statistically distributed. 1 mole is such a large number. Can't get any better statistics than that. I asked you already who doesn't have an eye clicker yet? I did, yeah? Okay, no? I didn't? You did, okay. It really doesn't matter. But I see the number is so low, that's why I'm worried. I see at least 250 people here. Okay. That's a statistical distribution, you see that? It's a Gaussian function, perfectly distributed statistically. So that means some of you are not sure. All right, otherwise we would have no statistical distribution. And let me help you a little bit. Let's assume I have a large number of red, same amount of red and white billiard balls in a big sack. I take one white out. Let's say that's oxygen 16. Remember, 16 I said is white. Oxygen 16. So I grab in there. I grab another 16. I grab a second time. Statistically, I grab an 18. 16 and 18 is evenly distributed. Now I take the red one, oxygen 18. I get there, I grab a white one, oxygen 16, and I go there statistically distributed, oxygen 18. So now try to discuss this with your neighbor and try to give me an answer. By the way, the homework has been posted on OWL. It is due Thursday, coming Thursday at 8 p.m. in the evening. You can come to any class you want. But you only can vote in one class. I mean, you can come to morning or afternoon, but you can't go to both classes and vote both times, okay? So I had this before. So you can vote in any class, but once a day only, okay? Not in one class. Okay.
How do you know how many, because this only keeps attendance, right?
Yes.
Is there a place to go online to see that?
Yes, I will tell you. Okay. I had a question concerning iClicker. When do you know if you are in and if you get your points? That will happen by next week. End of next week, you will go. There is something on BSpace then, isn't it? And you will get the results. We post it once a week then, okay, your results. So let's display that. Yes, we have 16% who are not sure about that, and one who is a good joker. And it's getting old, okay? If that happens, never mind. I'm not going to threaten you, okay? So, yes, that's the correct answer. I showed to you, I mean, the possibility, white and white in there, white, red, same probability. So you have that, and then you do red, white, red, same probability. So you get twice oxygen 18-16, and once oxygen 16-16, and one oxygen 18-18. So that's the oxygen 18-18, oxygen 18-16 twice as high than this one, and oxygen 16-16. So let me see if I give you the solution. Oh, I didn't give you the wonderful picture. So see, that's what you get. This is double, it's statistically distributed, and the answer was B. So let's combust some hydrocarbon. And we have here hydrocarbon. Of course, hydrocarbon is carbon and hydrogen. And we burn carbon and hydrogen with oxygen. Carbon and hydrogen and oxygen burning is combustion. That's how we drive our vehicles. It makes CO2 and water, right? Any carbon and hydrogen you can combust, essentially. Some better than others. And here we have here a hydrocarbon in there, and I shall combust it, okay? So let me, I'm the combustor here, okay? There you go. That was very different than the hydrogen explosion, wasn't it? Did you feel it up in the back, the heat? The small amount of hydrocarbon with the oxygen in the air made this incredible release of energy. That's how you drive your car, okay? And that's why the engine is warm. Right, so there is, now you take this, and we have collected this here. We could collect this. We don't let it go in the air or in the atmosphere. We collect it and put it through a through a mass spectrometer. And we get this kind of spectrum here, 18 to 44. And you're going to think about this over the weekend, and I will pose this question at the beginning of next lecture, and you will answer what the question is. The answer, Combustion of a hydrocarbon with oxygen yields products with the mass spectrum shown here. This here, which is the hydrocarbon? Methane, ethylene, or acetylene? Okay? So with this, I wish you a good weekend, and I see you on Monday.